All right, well, welcome everyone. I think we'll get started. So this is lecture 5. The topic of today's lecture is Dickson's lemma. So last week we were talking about the division algorithm. We're going to slowly start to build back to geometry. We spent quite a lot of time talking about monomial orderings, division, working with polynomials. And I want to start today's lecture by putting that in context a little bit. So we know that the basic objects of at least affine algebraic geometry are affine varieties. That is, solution sets of systems of polynomial equations. And to a large extent, geometry consists of understanding the relationship in the sense of does this variety intersect that variety, or is it contained in that variety, or where do they meet, or what is the dimension where they meet? Understanding the relationships between affine varieties. If you think about Euclid, the whole topic of the first book of Euclid is just about where lines meet circles, where lines meet triangles, the angles that they form, and so on. What algebraic geometry says is that in order to understand the relationship between affine varieties, we need to understand the relationship between their ideals. So recall the ideal I of V is the set of all polynomials which vanish on V. Now, as we'll show, as a consequence of Dickson's lemma and then the Hilbert basis theorem, these ideals are always finitely generated. Any ideal in the polynomial ring is finitely generated. So suppose we had two sets of generators, F1 through FR and G1 through GS. The most basic kind of relationship that can exist between two affine varieties is that one is contained in the other. And we've discussed a proposition 1.4.8, which says that V is contained in W if and only if every function that vanishes on W vanishes on V, which is a relationship between the ideals. Now, the ideal IW, if it's generated by the GJs, IW is contained in IV if and only if all those generators are. To say that Gj is in IV is to say that Gj can be written as a sum or equivalently that Gj vanishes on V. Okay, so we have these equivalent conditions. This here is kind of an algebraic problem. And the problem is ideal membership. So I want you to imagine that you've got the generators for IV and IW already. The question of how to find those for your given variety of interest is a separate problem. So suppose you have those generators and you want to check that V is contained in W. Well, you just have to check this. But how on earth do you do that in some algorithmic way? How do you tell if a given polynomial belongs to a given ideal? That's a non-trivial problem. That's the problem that's referred to as the ideal membership problem. By the end of the course, we will have solved this problem. At least we'll have given an effective algorithm for checking that one way or the other. This here is a more geometric way of checking. And depending on the problem, one or the other may be easier. Okay, so I'm going to give an example. So we're going to consider two lines in R3 in the plane, so in the xy plane, so z is 0. First we'll consider the line y equals x, and also the line y equals minus x, which is where those pairs vanish. And I'm going to consider the graph of x squared minus y squared, which is where this polynomial vanishes. Okay, so let me attempt to draw a picture here. So how am I roughly going to sketch this? Well, if I slice it in the constant x planes, that is, I stick a number in here, what am I going to get? Well, I'm going to get z minus some constant minus y squared is 0. So that's z equals c minus y squared. So as I vary c, yeah, I can do that direction first, but maybe I'll do the x direction first. So y direction. So if I fix a value of y, say c, then I have to graph something that looks like this, which is z equals x squared minus c squared. So it's a parabola that's moving down as I go out along the y-axis in either direction. All right, so that's x squared. I want to try and draw this picture well enough that you can believe that these lines actually lie. So I'll draw these in first perhaps. That's the line y equals x, and here's the line y equals minus x. So that's L1 and L2. All right, so that, now as I go out, they should go down. And then the y direction comes through like that. I think it's not so easy to get this in your head correctly, but I hope you can see the saddle there. So this surface that I'm drawing here is the vanishing locus of f. All right, so I claim that Li is contained in the vanishing locus of f. Well, there's two ways of checking that.
So what's happening?
Yep.
Dan, what's happening as you go down the x-axis? I understood what happened when you went along L1, but the parabolas going along the x-axis have me a bit confused.
Yep. So if I take a constant x plane, I'm going to be graphing z minus c squared minus y squared. So that's z equals c squared minus y squared, so it's an upside down parabola that is going up as you move away from the origin.
Yeah, no, so for the x ones, it looks like there's like some it looks like there's like here these are like upward parabolas going along the x-axis or something.
Oh, yeah, that's just like this one here, for example.
Yeah.
That's meant to be displaced that way. Yeah,
Oh, I see.
I
Okay.
think
Yeah.
yeah, you're right. This is just a bad line. It should probably be more
No
like
worries.
out here. Yeah.
Dan,
Yeah, yeah, okay, that makes sense then.
you should probably close and open the board to see some differences in what you're seeing.
Oh yeah, I see. Thanks. Yep. Yeah, those undos didn't actually undo.
Metavoid V0.
Yeah, that's right. Okay, so I claim, how would we prove those lines actually lie on that surface? Well, there's two ways. One is to show that I VF is contained in the ideal of Li. Notice that I can write this in the following way. Now it is the case that in fact these are just the ideals generated by those equations we started with. We don't have a good general mechanism for knowing that right now. Right, so all we know this inclusion automatically. You've seen in some examples it can be a bit non-trivial to check that this is actually equal. I'll leave you to think about how I can argue for this equality in this case, but I don't want to get too bogged down in this. I'm happy to talk about it later on. Okay, so how do we check that inclusion? Well, to check the ideal generated by f belongs to there is simply to check that f can be written as a linear combination of z and y plus those equations. But of course f is equal to 1 times z minus y. Why did I write it that way? It's quite awkward to have y minus x and x squared minus, yeah, okay. I hope this is right in the notes. Okay, that's not right, yeah, because if I multiply out those brackets, I'll get y squared minus x squared, so I need that to be a plus. Does that make sense? In order to match up with this sign here. The point being that this is something times z, the first generator, plus something times the second generator. So this proves that y is in fact, f is in fact in the ideal associated to the line, which proves those lines are on the surface. Okay, so that's one way, the way I called algebraic on the first board.
I think you missed an open parenthesis, Dan.
Really? Where? An open parenthesis.
Oh no, hang on, that happened when I opened the board, that's my bad.
Yeah. I don't pay out for V0 bugs. Okay, so the other way we can check is just to check that, so if I want to check this, it suffices to check that all the generators of this guy vanish on V. V in my case is the LIs. Okay. Or F vanishes on Li. I mean, that's clear from this expression, right? If you have a point x, y, z that makes both of those functions 0, then by that expression f also has to be 0. But you could also just check that directly. Right? If you have a point where on either of those lines, well, it looks something like, if it's on L1, say, a point on L1 looks like A, C. And it's clear f vanishes on such a thing. Okay, so that's an example of checking the relationship between two affine varieties, in this case a line and a surface. And okay, in this case it's kind of easy to see whether or not f is a linear combination of those generators, but in general we would have to do divisions. So we would run something like the division algorithm on f for the divisors given by that list of generators z and y plus minus 1 to the I x.
Do you mean AA0?
AA0. Oh, thank you. Yeah, I do.
Just to be sure, I understand. Like the V of f, visually it's supposed to be a saddle, right?
Mm-hmm.
Like what we drew on the board on the left, right?
Yep.
How? Like I guess we proved it. So my question is kind of dumb, but like a saddle, it has some sort of curvature in a way. How is it possible that the straight lines are inside the? Like,
yeah, that's why it's a good example. It doesn't. When you think about the saddle, it's not obvious from the mental image that it has this pair of lines in it, right?
Yeah, it almost seems false. Like, okay, well, I guess.
It gets wider and wider as you go away from the origin.
Yeah, one way to
what?
One way to accommodate your intuition to it is to think about the directional derivative of f along that line. So if you take the gradient of f, what's that? Well, rather the gradient of the function, which is, let's say f. It's a bit confusing. Take the function fxy is x squared minus y squared, and compute the gradient of f. That'll give you 2x, 2y.
2.
Oh, sorry.
Minus.
Yeah, minus 2.
Minus?
Yes.
Yeah. And so, okay, what does it mean again? The gradient, like the direction where f is. I mean, okay, it's the derivative.
Yeah, well, I mean, maybe this doesn't actually help very much. I mean, it shows you that if you evaluate it at 0, yeah, okay, the gradient's a bad idea. I didn't think about that properly. I think I mean, if you just look at the equation, it's sort of clear that y equals x is on there. But
yeah, right.
I guess you need.
But I don't know. Yeah, just visually, it's so weird. Like.
Yeah,
but I think I should plot it out or something and see that it actually is inside it. Okay, thank you.
All right. So, well, we sort of discussed a little bit the ideal membership problem and how that relates to seeing the connection between different affine varieties. So what about the ideal membership problem? How do you tell if a given polynomial is in a given ideal presented by a list of polynomial generators? Well, in general, that requires a new technique, Grosvenor bases, but there's a special case for which it's easy. A special case of ideals, a special class of ideals, and those are the monomial ideals. So what we're going to do today is I'll introduce the concept of monomial ideals, we'll prove some basic things about them, and the main theorem, the Dickson's lemma, will give us a kind of tell us that this is a finite problem, I suppose, is the best way to put it. Ideal membership for monomial ideals is a finite problem. I suppose this is something that sort of got swept under the rug in the discussion up until now, but it's all well and good if I have an affine variety with a finite number of generators. You might imagine doing division or something like that, but so far you have no reason to believe that I couldn't give a sort of interesting subset of affine space which is cut out by infinitely many equations. And how would I be able to somehow algorithmically tell its relationship to other things if I have infinitely many generators? All right, an ideal is a monomial ideal. If there exists a set of monomials this could be empty, could be infinite. Such that I is the ideal generated by that set. Now we know the smallest ideal containing a given set is the set of all linear combinations, so to speak, linear with coefficients which are polynomials in that set. So that is all things that look like, take some b alphas, and the b alphas are polynomials. Multiply them by the x alphas and add them all up. And of course we only take finite sums. Okay, so that collection is, it is an ideal, and if I is of that form for some monomials, then we say it's a monomial ideal, right? So this is not ranging over all tuples, just over the ones in this specific, well, indexed by this set A here being a subset of all tuples. So the ideal 0 is a monomial ideal. It's generated by the empty set of monomials. Is the whole ring a monomial ideal? The polynomial ring?
Yeah, sure. Just
Yeah.
have one of each variable, right?
Yeah, we can just take all monomials.
Yeah.
Yeah, that's right. Okay, first lemma. I mean, the first thing to say is it doesn't seem like monomial ideals should be very interesting, right? It's not obvious that we should care about these at all. Geometrically, they're not interesting at all, right? If I take the ideal, what, x squared, y cubed, z, that's a monomial ideal. And if I take the vanishing set of that, well, where does x squared vanish? It's just where x vanishes, right? Where does y cubed z vanish? Well, that vanishes where either y is 0 or z is 0. So you can see that this is the intersection of x equals 0. So just the yz plane with the union of y equals 0 and z equals 0. Okay, so a monomial ideal, its geometric form is kind of an intersection of unions of just coordinate hyperplanes. So that doesn't seem super interesting. So it's a remarkable fact that somehow we can reduce almost everything computationally to monomial ideals, where the monomials are leading terms of things. This is a really remarkable idea. Okay, so let's take a monomial ideal. Let's solve the...
Clarify something.
Yeah, go ahead.
So an example of a non-monomial ideal would have to be something that's like a interesting, like, linear combination of monomials.
Yeah, that's right. I mean, x plus y. The ideal generated by that would not be monomial. Yeah.
Okay, cool.
So the ideal membership problem for monomial ideals is easy. Let's start with a monomial. If I take a monomial, it belongs to the ideal if and only if it's divisible by one of the generators. Or equivalently, it's divisible by some monomial in the ideal. And finally, a general polynomial f is in the ideal if and only if every term of f is in I. Okay, so this means checking whether a given polynomial is in a monomial ideal is easy, I guess, as long as you have a finite set of monomials that generate. I guess it's worth saying that, of course, you could have two different sets of monomials generating the same monomial ideal. Right. What's an example of that? What's an example of two sets of monomials generating the same ideal? Get you started. Give me another set of monomials that generate that ideal.
X to the 4 and x to the 6.
Yeah, good. Or x cubed would do, right? I don't have to take some power of that. I mean, x cubed is already in the ideal, right? So adding that monomial doesn't make the ideal bigger. Okay, so these, you can have different sets of monomials generating the same ideal. Now, I could generate this with infinitely many monomials if I want, right? So this is generated by all the powers of x greater than or equal to 2. So that's an infinite generating set. There's also a finite generating set. So just because I happen to introduce a monomial ideal with an infinite set of monomials doesn't mean I can't generate it with a finite set. And we'll talk about that more in a moment. Okay. So given an f, if I want to check that it's in the ideal, part 3 of the lemma says, just go through every term and check whether it's divisible by one of the things in my generating set. And if that's finite, that will be an effective procedure for checking whether f is in the ideal. Okay, proof. So throughout today's lecture, we're going to write alpha less than or equal to beta for x to the alpha divides x to the beta, i.e. alpha I is less than or equal to beta I for all I. I want to I'm a bit sheepish about this, and I won't do it very often. It's just convenient for the proof of Dickson's lemma. The reason I'm sheepish about it is that this is not a monomial order. Right, this coordinate-wise inequality. Why is it not a monomial order? I mean, if it were, it somehow would seem strange to introduce lexicographic order. Isn't this the most natural order on monomials? Just division or entry-wise comparison? Why is this not a monomial order?
It's not total.
It's not total. Yeah, good. Right, so for example, x squared y and xy squared, that's 2, 1, and 1, 2. They're not comparable under that order. But they are under, of course, lexicographic order or any monomial order. All right. Okay, so for one direction is clear. Right. If x alpha divides x beta for some alpha in A, then x beta is a multiple of x alpha and therefore is in the ideal. So let's suppose that some monomial belongs to the ideal. Well, that means by definition that there's some expression like that for x beta in terms of the x alphas, where the b alphas are themselves polynomials, so let's expand them out. So that means they can be written as in this form, where the c's are in K. Right, there's nothing to do with A here. Right, I'm just taking these polynomials and writing them as a linear combination of monomials, where by linear here I mean with scalar coefficients. And now if I just expand, so gamma here runs over all tuples. So what's the point of this? Well, if you look at that expression on the right-hand side, it's a polynomial, and every term, there may be overlaps, right? In the sense that you may have gamma plus alpha equal to gamma prime plus alpha prime for some different pair gamma and alpha, gamma prime, alpha prime. But if you collect terms, that is, if you actually write the right-hand side as a polynomial, which assigns to every monomial a coefficient, so collect terms on the right-hand side, every term with a non-zero coefficient must be of the form gamma plus alpha for some pair, gamma and alpha, and maybe more than one, but who cares? So every term with a non-zero coefficient is divisible by x to the alpha. But that's a property of a polynomial that's independent of how you write it, which means it's also true of the left-hand side. I mean, a polynomial is just a gadget that assigns coefficients to monomials, right? So if the right-hand side assigns non-zero coefficients only to monomials divisible by x to the alpha, the same is true of the left-hand side. But the left-hand side assigns a coefficient 1 to x to the beta, which means that x to the beta must be divisible by x to the alpha. Okay. I'm going to skip 2. I think there's an exercise that basically covers some of this. And maybe I'll skip 3 as well, so I'll leave that for you in the exercises. It's pretty straightforward given what we've already discussed. It's basically the same. Any questions about the lemma?
Sorry, could you explain where alpha comes from? Because alpha is a bound variable.
Oh yeah. So what I mean here is, suppose x beta is in I, then by the definition, the alpha, it's sort of on the previous board, if you can see that, that's where the alpha comes from. So there must exist some expression of x beta in that form.
Yes, but at the end, like you conclude that x alpha divided x beta
Yeah.
certain alpha, right?
Yeah. You're right. Yeah, for some alpha. You're
Could
right.
you just re-explain where this sum alpha is coming from?
Yep. Okay, so if you look at this expression here, every term here, yeah, this is also bad. Every monomial with a non-zero coefficient. Every monomial in that expression with a non-zero coefficient is of the form x gamma x alpha for some alpha. That is, every monomial with a non-zero coefficient in that expression is divisible by x alpha for some alpha in A. And therefore the same is true of the left-hand side.
Because there's finally many of them.
I suppose that's involved. I'm not sure why you emphasize it though.
So, I mean, we showed that for every term there exists an alpha such that the monomial is divisible by x to the alpha, right?
Mm-hmm.
And then we concluded that there exists an alpha such that the entire sum is divisible by that x to the alpha. We switched the quantifiers. What happened?
That's one way to read what I said, but that's not what I'm arguing, because it's not clear that, I mean, in fact, that is true, but that's a little convoluted. Okay, so look at the right-hand side. It's a sum, but I don't want you to focus on that particular sum. What I want you to do, maybe let me add another line here, which I think will help. So if you collect terms, you can write this as sum over tau d tau x to the tau, where the coefficient here is sum over alpha in A and gamma such that alpha plus gamma is tau c gamma alpha x to the tau. So what I did here was collect terms, right? I said that, okay, if I look at these monomials, I'll get many different monomials, x to the tau, when I multiply these two. What are all the ways that I could contribute to a coefficient of some given x to the tau? Well, I'd look at all the terms in that sum which give rise to x to the tau. That is, I look for all the pairs alpha and gamma such that alpha plus gamma is tau, and I collect all those coefficients together. You guys with me?
Yep.
Okay.
Yeah.
Now those are the only monomials with a non-zero coefficient, these x to the taus. And every one of them is divisible by x to the alpha, because they're all of the form alpha plus gamma for some gamma, and some alpha in A. Now the property of whether or not you assign a non-zero coefficient to a given monomial is a property of a polynomial. It's not a property of a presentation of a polynomial. So since the right-hand side, this sum over tau, I mean, this is now a canonical expression of a polynomial, right? This is literally the coefficient it assigns to any monomial tau. And it only assigns non-zero coefficients to monomials divisible by x to the alpha for some alpha in A. But that means the same must be true of the left-hand side.
Oh, wait, so if... Well, is what we're doing, we're looking for the tau, which is equal to beta.
That's right. Beta must be one of the taus. That's one way of saying it. Yeah.
Right.
Yeah, I hope that helps.
Yeah, I thought you were like taking all the, like, it was like for all monomials there exists an alpha, and then you were somehow taking all those alphas and producing like one global alpha.
One true alpha.
Yeah, I see now, yeah.
Yeah, that's... Yeah. Thanks for those questions, guys. I can see how that is a natural interpretation of what I was doing, yeah. Okay. So we're ready for Dickson's lemma, I think. Let's move over. Oh, one corollary first. Maybe I'll just say it out loud. So two monomial ideals are the same if and only if they contain the same monomials. Why? Well, if you think about the lemma we just proved, well, obviously if two ideals are the same, I and j, say, and maybe I will write it. So corollary. Two monomial ideals, I and j, are the same if and only if they contain the same monomials. Proof? Well, if I and j contain the same monomials, then f is in I. Well, by part 3 of the previous lemma, to be in I means that every term of f is in I. But the terms of f are just scalars times monomials, right? So a given term of f being in I is the same as that monomial being in I. But I and j contain the same monomials by hypothesis. So that means every term of f is in j, which again by 3 means f is in j. Okay, so this means we can present monomial ideals and think about them. Via the set of tuples that index the monomials they contain. Just to be clear, that's bigger than the generating set, right? So if I take I to be the monomial ideal xy, right, so that's x to the alpha, alpha in A is just the singleton 1, 1. well, the set of all monomials in I, so if I take x to the beta is in I, if and only if beta is greater than or equal to, in that component-wise sense, 1, 1. Right, so it's i.e. x to the beta is x to the a, y to the b, a greater than or equal to 1, b greater than or equal to 1. And you can probably think of a natural pictorial way of thinking about that as a set of points in the plane. And indeed, we're going to use that picture in the proof of Dickson's lemma, and even a three-dimensional picture, which is the object behind you that I think I saw Richie asking about. That'll come in a moment. All right, so here we are, Dickson's lemma. This is theorem 2.4.5 of the text. It says, let I be a monomial ideal. Then there is a finite subset. A may be infinite, right? There's a finite subset, let's call it A0 of A, which generates the same ideal. Okay, this is A0. So the proof is going to be by induction on n, the number of variables. So let's think about the base case. We've already kind of thought about the relevant fact in the example I was mentioning earlier with x squared versus x squared x cubed. So in the base case n equals 1, well, the set of indices A is just the set of non-negative numbers, the powers of the variable, and that has a least element. Mu. And then it's clear that, well, if I take all the powers that are in A, all of them can be divisible by x to the power of the least one, mu. So that's just the ideal generated by x to the mu, which is a finite set of monomials. So the base case is easy. All right, what about the inductive step? Well, suppose the claim holds for n variables. And let I be a monomial ideal in a polynomial ring with one more variable that I'm going to call y. I'm not going to call them x to the alpha because that would be confusing since only some of the variables are denoted with x's. So I'm going to write the u to the alpha for the monomials. Okay, so if alpha is, the notation I'm going to adopt is I'll write something like beta m. So beta is in, this gives me all the powers of the x variables, so that's n, and m is the power of the y variable, so u to the alpha is going to mean x to the beta, y to the m. We're going to be using this notation a lot, so if this is unclear, please let me know. So x to the beta means x1 to the beta 1 dot 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 xn to the beta n. And I'm just dividing this tuple alpha up into two parts, the x part, which is beta, and the y part, which is just the integer m. So we're supposing given some potentially infinite set A of such tuples. Well, it would be good if that had a least element, and then we'd be done, right? So if A has a least element, i.e. there was some mu in A with u to the mu, divide u to the alpha for all alpha in A, then again we're done. That's a finite generating set. The point is that, unlike the one variable case, there's no reason for A to contain a least element. And the reason is the one that came up earlier. This least is with respect to division, and this relation between tuples or monomials is not a total order. So I want to think through an example. This is an example within the proof. Because to understand the strategy of the proof of Dickson's lemma, you sort of really have to see how you're adapting to this sort of failure of there being a least element. So let's consider the following example. Consider the following monomial ideal inside kxy. So that's I. So I'm going to color the part that's inside, that corresponds to monomials inside the ideal in gray in the following diagram. So these axes stand for alpha 1 and alpha 2. So vertices, so this picture is a plot of z2 greater than or equal to 0, right? So there's 0, 0, there's 0, 1, there's 1, 0, and so on. I might as well continue now. So each point corresponds to a tuple and therefore to a monomial, and therefore...
Dan, you wrote alpha 2 twice.
Oh, I did, thank you. So the set of monomials in I is some region in this plane. So x squared y squared is here, this vertex. X to the 4 y is over here. And anything which is greater than or equal to those pairs is also in the ideal, right? So everything in here, those are all tuples that are in the ideal, and similarly everything in here is in the ideal. Okay, so you see how these regions correspond to things greater than or equal to those generated tuples. Okay, so what's this point here corresponds to the fact that it's in those regions twice corresponds to these two relations of divisibility. Okay, what's the point of this diagram? Well, there's no least element, right? I have two minimal elements, x squared y squared and x forward y. There's no relation between them. Neither is less than or equal to the other. Sorry?
Just to be clear, x to the 4y probably should be across 1 to the right.
Oh,
if I understand correctly.
1, 2, 3. Oh, thank you. Yeah.
Okay, just checking.
Yeah. Yeah. There we go. Thank you. Okay, so those two sort of corners are minimal elements. In the sense that nothing is strictly less than them, in that coordinate-wise sense. But neither of them is least in the sense that they're less than or equal to everything else in the set of monomials. Okay, so what we're going to try and do then is try and argue along the lines of the n equals 1 case, but using minimal elements instead, and see how far we get. So remember, we're trying to find a finite generating set. I'll be more detailed in a moment, but you might kind of believe that we'd be done if we could prove that there's a finite number of minimal elements in A. And that's actually true. Okay, so we call u to the alpha in A, minimal if there is no beta in A distinct from alpha with beta less than or equal to A, which remember means u to the beta divides u to the alpha. And we're going to show that the set min A of minimal elements is finite. Now I want to argue quickly that that means we'll be done with the inductive step, and then we'll go on and prove that claim. So suppose the claim is true. Well, I is generated by all the u to the alphas. And I claim that it's sufficient to take the alphas that are minimal. Why? Well, if I take any u to the alpha in A, then either it's minimal, well, if it's not minimal, then by definition there's some beta not equal to alpha in A with beta less than or equal to alpha, i.e. x to the beta dividing x to the alpha. Okay, and then is beta minimal? If not, you can find something strictly less and continue this. Now, because there's only finitely many, at each point when you're doing this process, you're decreasing the sum of the entries of beta by at least 1. So it must terminate. So if you like, there's a little induction here. That should be u's. So we show there exists a beta which is minimal, and u to the beta dividing u to the alpha. Okay, so that justifies this equality here. And since the claim, if we can prove the claim that min A is finite, then we will have proved the inductive step, that I has a finite generating set of monomials. Okay, so we're going to move on to another set of boards to prove the claim. Actually, we'll go back to the first set of boards so we can use this 3D thing. But are there any questions before we move over there? Okay, seems not. So let's go back to the first set of boards. Yeah, just looking at the chat. I hope we don't get kicked off Roblox for talking about Dickson's lemma. That's going to hurt your head, Billy. Okay, here goes. To see the set of minimal elements is finite, we're going to compare, well, we're going to use the inductive hypothesis, right? That means we're going to try and compare A, this set of monomials that's generating I, to its projection onto what I'm going to call the x-plane. That is the first, not really a plane in the sense of two-dimensional, but the x variables. What do I mean by that projection? Well, I mean I take the set of monomials B in n variables. Remember, A involves n plus 1 variables, the x variables and that extra y. That is, B is the set of betas such that u to the beta x y to the m appears in I for some m. Oops. Why is that a projection? Well, let me draw a picture here and then I'll ask you guys to mirror it over to the 3D object, so you better follow what I'm saying now. Okay, so what do I mean by this projection? Okay.
Sorry, just really quick. When you say x to the beta y to the m is in I, do you mean in the generating set of I?
Ah, good question. No, I mean I, but that's of course related to being in the generating set in an interesting way, right? So if, yeah, so let's maybe dwell on that for a moment. So if x beta y to the m is in I, then by the lemma we proved earlier, that's equivalent to the pair beta m being greater than or equal to alpha for some alpha in A. Yep. Yeah, this is a good point. We'll have to dwell on this a fair bit. Okay, so let me try and draw a diagram here. So the base is going to be, so the base is the sort of x-plane. I'm going to draw two directions, which you could think of as beta 1 and beta 2, but really you should think about it as being higher dimensional than that. Okay, so here's a point in this plane stands for an x monomial, right? So here's x to the beta 1, for example. And here's another x monomial, x to the beta 2. Now in the three-dimensional, in the volume, I have monomials that involve also the y variables. Right, so up here, let's say I have x to the beta 1, y to the m1. And here stands for x to the beta 2, y to the m2.
Just to be sure, the beta 1 and beta 2 are unrelated to the beta 1 and beta 2 that appears on the, like beta 1, y, beta 2, you know, the axis.
Oh yeah, thank you. Yeah, they're meant to be kind of special cases of those, but I think that's better to just get rid of them. Yeah, thanks. Okay, so just as in the two-dimensional case I drew in the previous picture, if x to the beta 1, say, y to the m1 is in I, then any monomial which is divisible by that is in I. So if I were to draw I, which is a monomial ideal, so remember it's determined by the set of monomials in it, so I can represent pictorially that ideal precisely by coloring in this three-dimensional space, in grey, say, exactly those vertices which correspond to monomials in I. And if I did that in this picture, then I would have to fill in everything that includes, it's hard to see, that includes this vertex, but also anything divisible by it, which would be this infinite kind of cube going off in all directions that way, going off in all directions that way, and similarly here. But now the way these cubes interact, that is, where they intersect, can be more interesting. So at some point this cube, which is sort of in the foreground, meets that background cube. Okay? Okay, what I mean by projection is, I hope, clear now, right? So to say a beta such that there exists an m is to say that if you take this beta in the plane and look above it, you see some vertex which is actually in I. Does that make sense? Okay, I haven't been looking, but I hope you guys can now help me annotate this this thing over here. So let's pop over to the shape and let's see if you can see how it's supposed to correspond to that diagram. So I'll fill in the base, but I want you guys to fill in. So in the base here, this I'm going to draw on the ground. Let's see which corner is which. Yeah, that's that. Okay. Okay, so these axes here, those are my kind of beta axes, right? So this here is the kind of x to the beta plane. Does that make sense?
Hey Dan, can you hear me from here?
Yep.
You might want to tell everyone to detach.
Oh, good idea, yeah.
Being over here.
Yep. Where's the orb gone? There. Okay, everyone, for this part it's probably better if you detach from the orb, and we'll reattach in a moment so you can hear me when we're over here near the object. Yeah, thanks. Okay, so that's the x to the beta plane. Somebody please mark x to the beta 1 and x to the beta 2 in this diagram on the bottom, on the sort of x to the beta plane. Oh, I can see somebody's already... Yeah, so there's a few of these surfaces have boards on them, so I can see somebody's already marked x to the beta 2, ym2. Yeah, that's great. It's also kind of tiny, though. Can you maybe make it a bit bigger?
Yeah, it's sort of hard to tell how it's going to come out. The boards are a little hard to intuit, but I will do that.
Okay, good. So there's an x to the beta 2 on the ground. I can't see the x to the beta 1 yet. Oh, there it is, yeah. Okay, and we need an x to the beta 1, y to the m1 up on the other cube. So far, the blue thing doesn't have an interpretation in our story. That'll come in a moment. Okay. So, what are we trying to do with this picture? Well, remember, we're trying to prove the set of minimal elements is finite. So that's what I want you to try and visualize when you look at this picture. Clearly, these corners we've drawn are minimal. What does it mean to be minimal? Well, it means that there's nothing less than or equal to u, which is in the collection of things in the ideal. That's the same as there being nothing in A less than or equal to u, right, if you think about it. Okay, so in the picture, the fact that they're these corners means that they're minimal. Okay, so minimal equals corner thing. Now, how could there be infinitely many of these corners? Where could all those corners fit? And that's the kind of thing we're trying to prove isn't possible, right? So
Right,
how could we arrange
the y-axis? They could fit along the y-axis, right? But for them to be, so if we're thinking of this as like R3, then of course there could be infinitely many minimal elements, right? Because you could just keep stacking them in ever smaller, ever closer to the floor. And I guess the point is you can't do that because it's natural numbers.
Yeah, that's right. So they have to all be integral points. And why intuitively couldn't you just keep making them higher and higher? I mean, it seems like you could. You could stick another one in between these two white cubes that's a bit higher than both. And then you could sort of just imagine going higher and higher. But why is... I mean, of course, there's a proof to be done. But what I want you to get out of this lecture is kind of an intuitive understanding of why there's not enough room for infinitely many corners. Can you start to see some...
Dumb question, but if it's minimal in the 3D plane, doesn't that mean that its projection on the 2D plane is going to be minimal as well?
Ah, good question. No. Why?
Oh.
Think about the blue thing. The blue corner that's closest to you is minimal in the 3D space. If that were if that collection of points were in the ideal, that would be a minimal corner, a minimal monomial, but its projection is inside the shadow of the big cube above it. Yeah, it's a good question. It seems like when you first think about it that it might be the case that minimal things project to minimal things, but that's not the case, as you can see from the blue shape.
I mean, there's only a finite amount of room between the minimal points that you could stuff more minimal points in, and it's discrete, so you can't do it forever.
Yeah, but why couldn't I just keep stacking stuff out here forever? Whoa. Okay, I need to... Just give me a second. I think I still had all cam on and it just went nuts. Yeah, why couldn't I just keep stacking more cubes down the axes forever? I don't have to be between...
You're gonna hit the ground eventually.
Good, yeah. If I keep making them lower, I'm going to run out of room going down. Why can't I go up?
You make them... Well, you're going to run out of room going this way, or else you're not going to have a minimal element.
Yeah, good. Right. So I can. There's plenty of room up there, but I have to get closer to the bounding planes. That is the edges of my sort of where we're all standing over here, or the other edge. I'll have to get closer to that edge every time I try and stack a minimal element down these infinite sort of corridors you see between the current edges of the blocks and the coordinate planes. And that's true down here, it's true down there, and going up as well I have the same problem. So this is the core of the proof. So now it's just a matter of writing that down. So we'll come back over and maybe you can reattach if you wish.
So wait, we were saying that if you want to make the y coordinate larger and larger to like make more minimal elements.
Yep.
Like what's the statement about the beta like hyperplane? Like we're saying something like you have to get closer and closer to the origin, or closer and closer to one of the axes of the beta plane. Like it's clear in the 2D case, but I'm just trying to.
Yeah. So we're saying that if you tried to go up, you'd also have to go out somehow. Out meaning towards either of these. Maybe I'll draw it so if we look at the first board here, these two kind of bounding planes, which I'm drawing in green. As you go up and you try and stick a box, say here, it's going to inevitably get closer than either of these to those bounding planes in order for it to be minimal. And there's only finitely sort of many steps you can take in either of those directions before you hit it.
So that first box that you drew, that doesn't that's kind of gotten further from both planes than like the first 2 points we have. But after that point, like if you're gonna go up, you can't. Well, I mean, like, wait, I'm rethinking this. There's like you claim that the only strategy when you're going up is to like go towards one of the like beta planes, but I don't think that's true. I think you could like you make like could you draw that little corner again that you drew in green?
This one?
Yeah. I'm sort of imagining you could get further from like you could get not closer to either beta planes by like sort of doing the same thing, get like aiming for a point like in that new internal corner you made. Do you see what I'm saying?
You mean inside here? Or underneath it?
Yes.
Yeah, good. Okay, yep. Yeah, so you've hit on the reason why this isn't completely sort of obvious. I could make a little guy in here, right? I don't know if you could see that. This was like a little baby cube hiding under the shadow of the daddy green one. And that's not closer to either. That's actually further away. It's retreated into the shadow of that green one. Is that kind of what you had in mind?
Yeah, but I actually see two more spots, like here
Mm-hmm.
and here.
Yeah, good. Yeah, exactly. Now, you might think to yourself, well, that's kind of bounded by the green one in some sense, how much you can do that. I mean, the red ones, they don't really count because they've gotten closer than at least the green one to the planes, but not to the not than the original ones, the grey ones. So yeah, there's.
No, haven't they got further? So I increased y,
Mm-hmm.
but I went like further away from both planes.
Oh, I mean,
that's not minimal.
You can't be
contained in the green at that point, right?
You can't be inside the green one.
Wait, I'm trying to see the top-down projection. We have the green one there. Maybe I'm sort of rotated a bit. And then we have the other two cubes that look something like this. Am I drawing this correctly? Is that... Makes sense.
Yep.
And I'm picturing the red ones like slightly higher, but they're like here.
Yeah, okay, that's how I interpreted your drawing. Yeah, that's fine. They'll both be
And
minimal.
they're closer to the planes, right?
They're closer to the
So
planes than the
haven't I
green one, not than the original
Yeah.
grey ones, though.
Oh, right. Okay, yeah, they are closer than the green one. Yep, yeah, that makes sense.
But clearly it's not trivial to translate this intuition into an actual proof, right? Because as you're showing, it's not the case that you can't find minimal elements that are further away from both of those planes than the grey ones. For example, the green. And then relative to the green, the reds are closer, but they're further away than the greys. So what is the global kind of way of manifesting this intuition? It's just an intuition. It's not yet a proof. So I think that's...
I see how the orange one is a more important case because you are getting further away from both beta planes. But again, there's probably some argument about not being able to do that infinitely many times.
That's right. So there's the orange one sitting underneath there. Yeah, cool. I think this is a very good preparation for the proof now. Okay, I think we'll jump into it. Okay, so let's think about this projection. Maybe I'll fill in a little bit more in that picture just to put in the kind of plane or the region. This is the shadow of the grey cube above x to the beta 1, and this is the shadow of the grey cube above x to the beta 2. That's weird. Okay. Okay, so let's set J. J is going to be all the shadows of A, or the ideal rather generated by all the shadows. So that is x to the beta, beta in B. And this is in the polynomial ring of just the x variables. Let min B be the set of minimal elements of that. Now I want you to keep in mind that B was the shadow of everything in I, not just minimal elements, right? So what I drew in the picture was x to the beta 1, which was the shadow of x to the beta 1, y to the m1, which was minimal. But something out here, there's an x to the gamma here, which comes from something deep inside that cube, right? X to the gamma, y to the 1000, say. That's also something that belongs to B, that gamma. But if I ask for minimal things of the shadow, then they might have something to do with minimal elements of A, right? But minimal here means, i.e., there is no, minimal in a sense that only refers to the x variables. So there is no beta prime different to beta with beta prime in B and x to the beta prime dividing x to the B, x to the beta rather. Okay, so what's the relationship between min B and min A? So I want you to note, first of all, that minimal elements, we already discussed this actually, this came up naturally, that was nice. Minimal elements of A may not project to minimal elements of B. So if you take some u to the alpha, with alpha in A, then beta in B, certainly in B, may not be minimal. And the blue cube in the 3D shape illustrates this, right? So if I were to take that blue cube was meant to be kind of nestled down here in the first picture. So this, calling it x to the gamma, y to the k in the notes, and its shadow is something down here, right? This is x to the gamma. Now this is a little corner, it's minimal in A, but it's not minimal. Gamma is not minimal in B. Okay, however, if I start with a minimal thing on the ground, so if beta is minimal, then I can go upwards and find a unique minimal element of A. That is, there's a unique m greater than or equal to 0 such that the pair beta m is in min A. Let's see. Given the time, maybe I'm going to. It's kind of, I hope, seems reasonable. If there were two.
Well, it's a smaller if there were two.
Yeah, that's right. Yeah, you just go up. There's something in A which is above beta. Take the smallest one, and that's minimal. Yep. Okay, so we therefore have an injective map from min B to min A, which just sort of looks up. Right? Take beta, send it to the unique alpha, which is above it. Okay, now, by the inductive hypothesis, J can be generated by finitely many. That's the point of this whole projection, right? To invoke the inductive hypothesis. So this ideal J can be generated by some finite subset of the betas. And if you think about it, that means the minimal elements, they can only be divisible by themselves, right? So if every monomial in J is divisible by something in B0, the minimal elements have to be in B0. Okay, so that means that by the inductive hypothesis, the minimal elements of B is a finite set. So those corners in the shadows, there's only finitely many of those. Now we're still not done, right? Because some of the corners in the 3D picture, their projections are not corners in the 2D picture in the shadow. If it were the case that there was a one-to-one correspondence between the corners in the 3D picture, the minimal elements of A, and the corners in the 2D picture, the minimal elements of B, we'd be done. But that's not quite the case. So there's still more to do. I'm running over time. I apologize for that, but I probably only need 5 more minutes. So let's just get this done, I think. Okay. So what about these things like the blue gamma that don't map to minimal elements downstairs? Well, let's consider those blue guys. So let x to the gamma, y to the k be such that gamma k is in min A. Well, look at the shadow, gamma. That shadow is inside some grey square that's generated by a minimal element. right? By the same argument we saw earlier. If it's not minimal itself, if gamma is not minimal, then just keep subtracting entries, 1 from entries, until you find something minimal. Call that beta. Okay, well then by minimality, since, wait, I want to say, now look up. Right? Look up from that beta and find the minimal element of the 3D picture that's above it, the corner, the unique corner that's above that beta. Call that alpha. Now, since gamma is greater than or equal to beta, we must have k less than m. Right, because if we had k greater than or equal to m, I suppose this gamma k could actually be equal to beta m, right? So let me be in min. I suppose that's, yeah, that's actually fine. It's just a matter of presentation. I'm just hesitating about which I prefer. Let's stick with this. Okay. If k was strictly greater than m, then I would have that gamma k is strictly greater than beta m, which is alpha. But that contradicts the minimality of gamma k, right? Gamma k was a corner, so that can't be. Now, what's the point of this deduction? Well, there are only finitely many of these, and to each of them I can associate this integer m. And k is less than or equal to that m for that beta, but I can take the maximum over all of those. All right, so to come back to this picture for a minute. So here's where I'm leveraging the finiteness of the inductive step. Right? I look at each of these corners in the 2D picture that I just colored in green. I go up and I find the heights, m1 and m2. There's only finitely many of these. So I can look above all of them and take the heights and take the supremum over that finitely many heights. And I'm going to call that capital M. Okay, so let's say let M, well, maybe let's write it like this just to spell out what I said. So suppose the minimal elements of B were beta 1 through beta r, and that the heights are m1 through mr. And let's take m to be the maximum of all those heights. Okay, then we've shown that if gamma k is in min A, then k is less than or equal to m. Okay, so these corners we were drawing in the orange and the green and the blue, they can't go arbitrarily high. Every corner is at a height less than or equal to the height of the highest gray cube. That's by the hypothesis that there's only finitely many shadows, or minimal elements in the shadows, in the set of shadows. Okay, so now we're almost done. We still have to account for all those colorful cubes, right? So that we do by considering each height one at a time. So in any given y slice, we can only have finitely many minimal elements, that is finitely many corners. Because for any of these valid heights, k, we just sort of run the same argument that we did for the finiteness of the number of corners in the plane. We just apply it to these other slices that are above height 0. So let me take the betas, where x to the beta, y to the k is in I, and let jk be the ideal generated by those. Then again, by the inductive hypothesis, min bk is finite. Same argument as before. And if beta is in min bk, there is a unique, you can look up, there is a unique m such that beta m is in min a. M may not be equal to k. Right, because here, just because x to the beta y to the k is in I doesn't mean x to the beta y to the k minus 1 isn't also in I, right? So you could have that beta being in bk minus 1. So if you look up, you may hit height. I mean, the true corner above beta may be lower, but it's definitely not higher. Okay, so we have a family of injective maps. You can look at the corners on the ground and look up to get a minimal element of A. You can look at the ones at height 1 and look up to get an element of A, and so on. So this is the map that sends beta, one of these corners, but for the things that live at height k, sends it to the associated tuple, associated corner above it. And the claim is that every gamma k in min A is in the image of one of these maps. Then we'll be done, right? Because these are all finite. So their images are all finite. And if you take the union of all their images, that'll still be finite. So if everything is in the image of one of those maps, then min A itself must be finite and will be done with the inductive step. Okay, so I just have to convince you that every gamma k is in the image of one of these maps. Well, if gamma k is in min A, then let beta less than or equal to gamma be in min bk. We know that gamma is in bk, right, by definition. So it's either minimal in bk, or we can decrease it until we find a minimal thing. And this, you can think about the blue cube, for example. Now, if beta is not gamma, I mean, you can decrease it to a minimal thing. If you actually made a change in order to do that, then we'd have x to the beta y to the k in I. That contradicts minimality of gamma k. Right, because x to the beta y to the k divides x to the gamma y to the k. But that's impossible by minimality unless beta is equal to gamma. Well, that means beta must be equal to gamma. But that means that gamma k is exactly the corner that's associated to a minimal element gamma of min bk. So it's in the image of one of those maps. And therefore, everything in min A is in the image of one of those maps. And so min A is finite. And so we're done with the inductive step.